Okay, so welcome everybody, and this is actually the third session of the class, the PV class. Hopefully, all of you, if anyone has any issues with the online portion, let me know because we want to make sure you don't just drift along there. It should be working. I haven't heard lately of any audio issues. Sometimes that was one where depending on the browser or the version of the browser, you might have the audio kick off. Hopefully that's not a problem. You should, just to gauge yourself, be through um, chapter 6 or into chapter 6 now. Or sorry, no, chapter 5. Um, so if you're not, catch up. If you are, great. You can go ahead. You can move ahead if you want.
Rounding conductor will be green
Okay.
with yellow stripes.
All right. Okay, so all right, so let me go ahead and first off open it up. Does anybody have any questions as you were beginning to as you're going through the online course or the textbook or Life, the Universe, and Everything? Anybody have any questions that you would like me to try and answer as we get
I
started?
have a question. This is Cliff.
Okay.
On uh chapter 3, there is three questions at the end. If you could go over those real quick, that would be awesome because I was having a hard time figuring out the math. It's the one that says Oscar is conducting a load analysis on a barn.
Yeah. Uh-huh.
Okay.
Okay, well, one thing I'll put your mind at rest. There will not be a question like that on the test, but that said, let me just show you the easiest way of doing it. Let me see. I know they've got a white screen here. Yeah, whiteboard. There we go. All right. So the easiest way of doing this is just really to do a grid, an Excel spreadsheet. So what we're dealing with here is there are three loads. So we're really talking about um, uh, variable loads because it's easy to figure out load demand. If you've got a load like a 60-watt light bulb and it takes 60 watts while it's running, and if you run it for an hour, that's 60 watt hours. If you run it for 2 hours, it's 60. It's 120 watt hours and so on. And then you just figure out how long you're going to run it each day. Boom. But sometimes you have loads that only run occasionally. And how do you allocate that over the days? So that's kind of what we're dealing with here. So we're saying, okay, there are three different loads, three critical loads here. There's a water heater. There's a milking machine. And then there's a grain dryer. All right. So if you just break it into a grid and say, all right, well, how many watts does it take when it runs? And how many hours per day? And then how many watt hours? So, which is just going to be a factor of those two. You'll just multiply it, and that's watt hours per day. So we could say, all right, well, the hot water heater uses 1,700 watt hours per day. So it's giving us this number. And then it says, and it runs 4 hours each day. So we have that. So assuming there are no loads. Well, before I figure these things out, we'll just fill in what we know. The milking machine uses 900 watt hours per day and it runs for 3 hours. And then the grain mixer, it uses 1,200 watts when it runs. And this is the confusing one. It operates for 2 hours twice a week. So we could just say that's going to be 2 times 2 divided by 7, right? 2 hours twice a week, 7 days in a week. And so if we just want to figure that one out first, that would be 4/7. We could decimalize that. Let's just say 0.57. So 0.57 hours per day on average. So 1200 times 0.57 is going to give us 685, 686 watt hours per day. The milk one, we can figure out 300 here, just dividing 900 watt hours per day by 3 hours. So we know it takes 300 watts to run. And then here, 1700 divided by 4, that's going to be what, 425? So we're just filling in. This is going to be watts. These are hours per day. And then these are watt hours per day. And then the first question says, okay, what is the daily load demand if these 3 critical loads are the only loads in the barn? Well, then the daily load demand just going to be the total here. So that's going to be 26, 32, 86. And that's answer A. Then question 23 says, assuming all the machines can be operated at the same time, what's the maximum power draw? Well, the maximum power draw is the instantaneous in watts draw if they're all running. So that's going to be 1925 watts. So that answer is going to be B. And then it says, assume only one of the machines can operate at a time. Well, then it's just going to be the biggest one. Right? So then that answer is going to be 1200. So does that make sense?
Yep.
Yes, thank you. That was great clarification. I appreciate that.
It's easy to do if you just do it in a grid. And this is part of what you would do when you're doing a daily load, assessment. And why are we breaking it out by watt hours per day when we talk about our daily load? And that's really simple. It's because the sun rises and sets on a daily, by definition. So, that's so we say, okay, what am I using each day? Because my solar array is going to replace power on a daily basis. So if I had one big load that only ran once a week, but I've got 7 days to build that back up, then I only need to generate 1/7 of that load on a daily basis in order that over the course of the week, I've made up the shortfall. If I'm connected to the grid, I'll just go into deficit that one day and then pump power back to the grid every day because I'm generating a little bit extra, and that will get me to zero at the end of the week. If I'm a standalone system where I've got batteries, well, that might be a little bit more complicated because if it's once a week, well, we know our battery better be able to supply that load, and then we're going to recharge the battery over the course of the 7 days. But what if it operated twice a week? And then you start thinking, okay, is it Monday and Tuesday? Because then I better have enough that they're both met. But if it's Monday and Thursday, I could get by with a smaller battery because I'm going to have replaced some of it in that intervening couple of days. So you can get more complicated as you're trying to size these systems. In reality, we don't run into that very often, but something to consider, especially if you're dealing with an agricultural situation, a remote situation, where maybe they're going to run a big load, but only infrequently. A good example would be a grain dryer. We run into that a lot on farms where they just run the load and it's always going to be run just in August or September or whatever. And it takes a huge amount of electricity. Well, there we're not talking about load demand per week. We would say, this is the load per demand over the course of the year. And now let's divide by 365, for instance, and then we'll get to what our daily requirements are for the solar array. Something like that, I wouldn't recommend trying to do off batteries because you're going to have some pretty hefty batteries. But you can use the grid and then over the course of the year, build up a surplus, use it all in September or whenever they're doing the grain drying, and you end up at zero. So that's a good example of a fairly common variable load. Any other questions from chapters 1, 2, 3, 4, or 5?
I think I have a question. When you run it in series and parallel, now is that now I understand the whole series where the voltage increase and the amperage stays the same, and then the series, the opposite, the voltage or the voltage changes or the amperage goes up in
When you do
parallel.
it in parallel. Yeah. When you do it in parallel, amps increase, but voltage
Right.
remains the same.
Right. And now, is there any correlation? Is that just like to the system that you want to design, or does it have to do with shading or something like that? I feel like I'm missing something.
Yeah.
Um, because
Typically it doesn't have to do with shading.
yeah, shading is that okay?
Yeah, it doesn't. What the reason why you worry about voltage and amps, well, voltage specifically. Why would I care if the system is 12 volts, 24 volts, 48 volts? When you're dealing with something like that with batteries, it usually has to do with what is the load demand. If we're dealing with 12-volt appliances, then my system's going to be 12 volts. But if I have a 20 or 48 volt load demands, let's say my lights that I'm operating operate at 48 volts, for example, then I better have my configuration created in series to meet 48 volts. So we do our series connections to get to the voltage that our load is going to want to see, that it's going to want to operate at. Now, if it's a grid tied system, we're typically, let's say we're an off-grid system. Um, the the loads are typically going to be run from an inverter. That inverter is going to generate 120 volt or 240 volt AC electricity. So we're not really looking at the load there. Now we start going and say, well, what is the voltage of the inverter? That's what I'm feeding from my array. So that's something that we would look at. And most of these standalone inverters are going to be like 48 volt systems. Why are they 48 volts? Well, historically, you could not have batteries in your home that exceeded 50 volts DC.
Mm.
So that was just a national electrical code requirement. So they just didn't make inverters that were more than 48 nominal volts, 50 volts. So because then they would have exceeded the law. So 48 volt was sort of top end. That's
Right.
changing now. It's changing because companies like Tesla went in and lobbied and said, "Hey, we've got these batteries here, and you're saying we can't have more than 50 volts. Well, we're coming in from a solar array that's 600 volts. We have to step it down to 48 volts, and then we got to step it back up to 240 volts for our household. It's very inefficient. The wires are bigger and all of that. Couldn't we increase the size of the voltage?" The NEC was like, well, we think it's dangerous, that consumers might have access to these higher voltages in their homes. Tesla goes, listen, you got to be an authorized, trained Tesla installer in order to work on this thing. None of the terminals are accessible by the end user. So shouldn't we be allowed to have higher voltage? And the NEC, I think it was in 2017, said, yeah, you know what? You make a good point. Sure, as long as they're inaccessible, as long as it's part of an assembled system, you can go to whatever voltage you want to go to because your technicians can handle it. Then a few years later, they came back and said, wait a minute, we were a little bit too generous with this whole go to whatever voltage you want to go to. We should at least limit it to whatever the voltage is of the building that you're installing it in. So if it's a residential, you can't exceed 600 volts, just like you can't with solar panels. If it's a commercial, you can't exceed, what is it, 1,000 volts or 1,500? I always get those two confused. Either way, so most of those systems now, most of those battery banks that you see, like a Tesla Powerwall, I think they're in the 400, 450 voltage range. That's kind of where they're at. But historically, we always said no more than 50. And on the test, if it asks you what size battery, what's the maximum for the battery, say 50, because they're still catching up a little bit. So, so say 50 on that. So if I share let me just sort of show so where it really comes into play, here we've got a system. So we've got our solar array here, and we're going to come into, and the next piece of equipment that we come to, or the next in the series, is going to be a combiner box or a junction box. That combiner box or junction box is usually going to be located underneath the array. So visually you don't see it. Unless there's a ground mounted system, then it might be on the pole on the back of the array, whatever. Now, the only difference between a combiner box and a junction box is that the junction box, you do not make parallel connections inside. You would just run the strings on there'd be multiple strings. So for example, let's say I've got 3 strings coming in from my array. In a combiner box, I would combine those in parallel, and then I'd only have 1 string leaving to go to my DC disconnect. It'd be a bigger wire, and the amps would be more, because when you connect in parallel, amps go up, voltage stays the same. But in today's world, typically you would have 3 strings coming out.
Right.
It would just be a transition point for your wire, going from the more expensive PV wire to the cheaper wire. And the reason we have 3 strings coming out is, of course, first these things would go into a DC disconnect, and the DC disconnect, it would require you have 3 connection points for disconnection, or actually 6, counting positive, negative 3 times. So it gets a little bit more complicated in the DC disconnect switch. And then you go into your inverter. These are usually now part of the same unit. And the reason for that is this inverter might have 3 MPPT control devices, the maximum power point. So you remember from our last discussion, we want each string then to operate independently of the other string. So they're going to be at the maximum power point. So if you get one little bit of shading over here, it only affects 1/3 of the array. It doesn't affect all of it. If I combine them, it affects everything. It's all going to just have one maximum power point. So, all right. So then let's assume that I'm dealing with just a combiner box, right? So I've got my combiner box, and I'm going into this DC disconnect. So let's see, what were we on? I just lost my train of thought. Well, let's finish the drawing. We go from here, and we're going to go to an AC disconnect. Now, the AC disconnect is considered the main disconnect for your PV system. And as such, it's got to be located within 10 feet of your meter. So it's got to be outside. It's got to be located within 10 feet of your electrical meter. It's got to be externally operable. So basically, it's got to have one of those blade switches on the side so that the people who use it don't have to go and get a tool and open it up to turn it off. And it's got to be well marked. And the reason for this is, let's say that your house is on fire and the first responders come. The first thing they're going to do is go to your electrical meter, and they're going to pull that meter. That meter acts like a fuse. If you pull that thing out, it's disconnecting the house from the grid, because they don't want to have any electricity in that building as they're bashing through walls and cutting holes in the ceiling to vent smoke. They don't want to cut into any live wires. So they
is that a transfer switch?
No, it's manually done. They'll just pull your meter.
Oh, okay.
When you pull that meter out, that meter measures the electricity that's being drawn in and actually going back out. But if you ever pulled it out, there are like 4 slots that fit in, and it's acting just like a fuse. When you pull that thing out, you've disconnected the home from the grid.
Okay.
But on that meter, there's going to be a little sign that says, whoa, wait a minute, there's another source of power here. You better turn that off too. So you're
Right.
going to go over and they'll look around. Well, they say that's why within 10 feet, because they'll see it, they'll go over and it says this is the main disconnect for the array. So they turn that off as well.
Okay.
So that's now they think there's no power in the building. All right. So that's why, and this goes out here to the telephone pole, to the transformer. Now from the AC disconnect, we would come into your service panel. We would hook into the double pole breaker here, and then this would be your main, and that main then connects over to the meter. So that's what a standard grid tied string inverter system of old looks like.
Okay.
Now, what I just told you, as far as let's say that the house is on fire, they come and they pull this meter. Well, immediately now your system is disconnected from the grid. So your inverter should come equipped with anti-islanding, which basically means it's going to shut off as soon as it loses sight of the grid.
Oh, okay.
It should do that anyway. But then just to be sure, because the NEC doesn't trust automated things really, they say,
Smart.
okay, let's put a disconnect switch there just in case.
Yeah.
So you turn it off. Well, now for sure that inverter is shut off. But if it's still sunny, it shut off the power, so it's no longer generating AC. But all of the lines going from the array down to the inverter are still live if the sun is shining. You know, that's DC, right? They're still hot and they could be 600 volts.
Right.
So if I've got a building here, let's say my home is like this and I've got the solar array up on the roof and I've gone through the attic and I've gone outside and I went down into the basement. So this is show you how good my drawings are. And then we go into the basement and down here is my inverter. Well, all of these lines going through here could be live 600 volts.
Right.
So a fireman climbs up on the roof and chainsaws right through that wire and gets killed because they've just cut through a live wire. So in 2014, they came out with what they refer to as rapid shutdown. And it went through a number of changes, but it basically says now, whenever you turn off that AC disconnect that's right out here, we want the power to shut off at the array.
Okay.
And the only way that could happen, well, if you think about it, the first solution was, okay, well, where does the power shut off? It shuts off at the inverter. So let's just stick the inverter right up there next to the array, you know, and that's fine if you're doing this on top of a Walmart or something like that, where you've got a big flat roof and you can just set that thing right there next to the array. Now it's all pretty apparent. But if it's a regular old shingled residential home, you don't want to put a 80-pound piece of equipment up there on the shingles. It's going to look weird. It's going to not do well. It's just not practical. So then a company called Enphase, well, Enphase said, instead of making one big inverter, let's make little tiny inverters that hook up individually to individual panels. So I'm going to put my little micro inverter and I'm going to attach it there. And this panel, one micro inverter.
Right.
And at that point, yeah, as soon as it loses sight of the grid, it shuts off and it shuts off right at the panel. Problem solved. the only problem was these things were kind of pricey,
Yeah.
like $200 a piece or so. So if I'm putting up 20 of them, I just spent $4,000 on these little microinverters where I could buy a regular inverter for maybe $2,000. And, the bigger the array, the more expensive it gets, and so on and so forth. So then a company called Solar Edge said, you know what we could do is instead of putting the whole microinverter, the whole inverter up there, we'll just get a little piece of electronic device and let's stick it up there that has rapid shutdown, have the anti-islanding at the
Mm,
panel, and then have an inverter that it connects to.
mm.
Well, also, I should have pointed out when you put the microinverter up there on the panel, you got a couple of interesting benefits because every panel now has its own MPPT. So every panel acts independently of every other panel. So if you get shading on one panel, you're only getting shading on one panel.
Right.
So that was very nice. And then they said, oh, you know what else? We have a communication device in here. So now you can monitor each panel. And so if something happens with one panel, you know exactly which panel it is. It's telling you what it's producing. It's giving you a lot of data. We like that. And people did like it. So you've got the rapid shutdown provision, the anti-islanding. You've got the MPPT. You've got the communication. And then you've got going from DC to AC, all happening right there at the panel. Solar Edge said, well, we'll do all three of those things, the anti-islanding, the communication, and the MPPT, just not the inverter. And we'll call it a power optimizer. And we can produce these things for like $50 instead of $200. So that became another option. All of this was in response to the rapid shutdown provision saying we need it to turn off at the panel. Well, it's turned out that this was a good solution. And today, about 90% of all residential systems are either going to use microinverters or power optimizers.
Okay.
So it's just a better solution at small scale, at
Right.
residential scale. When you start getting into massive systems, probably not. But any system that's on a building has to have an electronic device attached to the panel.
Okay.
We call those module level power electronics, MLPEs.
Mm.
An optimizer is one. An inverter is a microinverter is another one.
Yeah.
So, all right. So now we've got this system here. So we want to size the wire. Okay.
Right.
So how do we decide? Well, before we get into that, I haven't touched on voltage drop, have I, in these presentations? Did we talk about voltage drop at all before?
No. No.
No, I
Okay.
don't think so. I have one question though, is on the MPPT, right? If you have two different strings, same voltage, but different current, like what is happening there if there's a mismatch in the currents? Like, are you just combining them at the MPPT and it doesn't matter? Or like if it's parallel, are they just adding to each other, but it's all on one string? That's the question I have
Yeah.
are you doing one string, but let's say there's two different voltages on two strings to one? That's kind of where I'm confused on the MPPT part.
Yeah, if you're
You know what
connecting
I'm saying?
into an individualized MPPT, they can be different. They could be slightly different voltages, slightly different amperages for sure. You'd have to just check the specs on the inverter that you're connecting to. That's one of the advantages of like a microinverter is you could have different sized panels. You can have one 300-watt panel,
Right.
one 350, one 325s. They could all be mismatched and they act independently. So the output is going to then be 240 volts AC and whatever the amps are, depending on what the input is. With these string inverters, if they've got multiple MPPT connection points, I think that they will likely act independently of each other. There will be a maximum. They can only deal with so many amps, but I think they could be different.
Okay.
It's going to depend on the equipment though.
Okay.
All right.
Okay.
Okay, so let's use this example. Well, let's talk about voltage drop. So what are the three equations you have to worry about? Well, the first one's pretty straightforward. Watts equals amps times volts. So you should memorize that, tattoo it on your arm, whatever you want to do. That's just saying that there is a relationship between these three things. Watts equals amps times volts. And in the water analogy, we just say watts is the amount of water flowing through the pipe, amps is the size of the pipe, and volts is the pressure under which that water is flowing. So you just say, all right, and you can measure water pressure without water flowing. You know, you can do that. You can measure volts without electricity flowing, but you cannot measure amps. You cannot measure current unless it's going somewhere, unless it's flowing to a load. So without a load, you cannot measure amps, right? Because there's no flow of electricity without a load. Okay, but you can measure volts. If you just, stuck a meter into a wall outlet, you could measure and it would say 120 volts. But if you stuck the same meter in there and tried to measure amps, you get 0 because it's not
So it's just
servicing load.
whatever's drawing the amps, right? So
Right.
it's just whatever device is pulling it out, right?
Right. And it will vary depending because the load is what's going to govern how many amps are flowing up to whatever the maximum the system is designed to handle, at which point a circuit breaker would trip because you've exceeded the capacity or you're getting close to exceeding the capacity of the wire. So you put an overcurrent protection device in there to keep that wire from burning up. So you just want to have an identified, easily accessible point of failure, which is what your circuit breaker is. And then you can reset it after you've removed those loads. So that's all a circuit breaker is just a weak point in the system. And it's designed to fail. All right, so the second equation you need to memorize is VER, volts equals amps times resistance, and that is Ohm's law. Again, it's just saying there is a relationship between these three numbers. If you know two of them, you can figure out the third one. And the analogy I use here is if amps is the size of the pipe and volts is the pressure, then resistance is the friction within the side of the pipe as the water is flowing through. And over distance, you're going to lose some of the voltage because you're going to lose some of that due to friction. And that friction is going to show up in terms of heat because energy is never created or destroyed. So then we get into the third equation, which is a variation of Ohm's law. And that's voltage drop equals amps times resistance times twice the distance divided by 1,000 feet.
Right.
And why are we doing it twice the distance divided by 1,000? It's because we're given resistance in ohms per 1,000 feet. So if I look up in the table and it tells me that 10 gauge stranded copper is 1.24 ohms, that's ohms per 1,000 feet. So what portion of 1,000 feet am I talking about? And the table that I'm referencing is on page 92. So why do we say twice the distance? Well, it's a circuit. It's a circuit. So there's wire there, wire back. So that's how far the electron is running. So let's say in this example that I've decided to use 10 gauge wire, and this here is 280 feet from the combiner box to the DC disconnect. So it's a long way off. And I'm using 10 gauge wire. So I want to know how much voltage am I losing from here to here? So my equation says voltage drop equals amps. Well, what are the amps? In this case, I would look at the IMP on the solar panel because that's the actual amps. And let's say that the panel that I'm using shows me that I have an IMP of 9 amps. and I've got 10 of them hooked together in a string. So in this array, I've got 30 panels. I've got 3 strings of 10. Well, what is the ampacity of one string under this scenario? I'll let you guys answer. If I've got 10 panels, a single panel has an amperage of 9 amps. I've hooked them together in a string, which is a series connection. What's the amps of the string?
Oh, it's still 9, right?
Right,
It's
because
still, yeah, just the voltage is added.
the voltage goes up. You know, if the voltage was, if the VMP on this was, let's say, 35 volts, then my voltage of that string is going to be 350 volts, but the amps are still going to be 9 amps.
Right.
So I've got 9 amps for each string, but I've combined 3 strings in parallel right here in my combiner box. So what is the amperage for this particular wire here?
It'd just be 9 times 35.
Not 35.
9 times 27, 9 times 3, right?
Right, 27
3
amps.
times the amps combined.
Right, because I've hooked 3 strings together in parallel. So when I do parallel, now it's going to be a 27 amp system, still 350 volts, because voltage didn't change. So I now know my amps, 27 amps. Voltage drop is resistance. I said I'm using 10 gauge wire. So you look up in your table on page 92 and you see 10 gauge wire stranded is 1.24 ohms per 1,000 feet. Well, what proportion of 1,000 feet am I talking about? It's 280 times 2 divided by 1,000. That's going to be 560 divided by 1,000, or 0.56. Everybody see that?
Yeah.
All right. So then we do the math and we say 27 times 1.24 times 0.56 gives me 18.75. 18.75 volts. So it's saying from here to here under this scenario, I'm losing 18.75 volts. Well, is that acceptable? Well, first off, if this were an 18 volt system, which is not going to be, I'd have lost it all. I wouldn't get any power down here. I wouldn't get anything because I just lost all of my voltage due to resistance from here to here. And this is pretty much the problem that Edison had back in the day when he was using DC current, because he couldn't ramp up the voltage easily. So he had to put substations to regenerate it every 6 miles. So Tesla, with his AC power system, said we can increase the voltage and then we overcome this voltage drop issue. So, all right, what did we say is the voltage of the system? Well, we know it's 10 panels through 35 volts, so it's going to be around 350 volts. So if that's 350 volts and 18.75, that gives me a little over 5%, right? Is everybody seeing that?
Yeah.
It's I'm showing 5.3%.
Yeah,
Is
we want to stay under 5.
Yeah, and I'd really rather be closer to 2.
Yeah, too.
So what are my choices?
We could shorter the distance of the wire, maybe.
I could shorten that, but you should have done that in your original design, right? You should make it as short as you can make it, because you don't want to be spending money you don't have to. So hopefully your design is already pretty clean there.
Could you
So our
use a bigger gauge wire?
Bigger wire, we could do that for sure. So what would happen? Let's say that I pick 4 gauge wire.
Volts.
So I go to 10 gauge. I go from 10 gauge to 4 gauge. What's the ampacity or the resistance of 4-gauge wire. Looking at page 92.
0.308.
Yeah, 0.308. So instead of 1.24, it's 0.308 ohms. So now I could just figure this equation. It's 27 amps times 0.308 times 0.56 gives me 4.65 volts. 4.65, yeah. So 4.65 divided by 350. And I can already see that's going to be what, about 1.5, right?
Yeah.
Yeah, 1.33%.
Hmm.
So that works, right? That all
Right.
works. Problem is we just spent some money, right? Instead of 10-gauge wire, we just put in 4-gauge wire. So instead of spending about 20 cents a foot, we probably spent about $1 a foot times 280. All right, so we spent another $500, something like that. Yeah, you do what you got to do. Maybe a better option would have been, let's look at the voltage. We can, instead of having 3 strings of 10, what if we do 2 strings of 15? Are we going to exceed our 300, our 600 volt? Well, we'll have to do some other calculations, but 35 times 15 looks like it's going to be well under. It's 525. We're going to have to do some temperature adjustments and things like that, but let's just assume we can do it. So now we've got 2 strings. Well, 2 strings, now our amperage is, instead of 27, is now only 18. And our voltage is 525. So going back to the 10 gauge, let's see what would happen. I just say 18 amps times 1.24 times 0.56 gives me 12.5, and 12.5 divided by 525, which is the voltage, gives me just over 2%. I could make that work if I had to. So just reconfiguring from 3 strings down to 2 strings, I might have solved my voltage drop problem. I'd probably still, instead of 10-gauge wire, want to go to 8-gauge wire, but I don't have to go to 4. So these are some of the considerations you're going to be doing as a designer. You know, you want to push your voltage up as close as possible to 600, because now we've saved some money on this system by going to 2 strings. We don't have to have as much, if we're putting in breakers or fuses in this junction box or in this combiner box, each of those breakers is going to cost you $20 or so. Well, we've just reduced it. Instead of needing 6 of them, I only need 4. So I saved, $40 there. I saved on the wire size. So I saved some money there. So pushing it up to 600 volts, as close to 600, is going to save you some money. It also is going to reduce the issue of voltage drop, or the impact of voltage drop. So that allows us to get by with smaller wire. So it's always a bit of a balancing act if you're doing this.
Yeah.
Will different townships and municipalities make you use 3 strings, or would they let you do 2 strings?
As long as you don't exceed 600 volts, they'll be fine. But remember, it's not 600 volts standard operating. It's 600 volts under the worst conditions that will ever be experienced at that location. So when we get into chapter 7, we're going to see, when we start to do string calculations, you've got to factor in, well, what's the coldest day that site has ever experienced? Because the colder it is, the higher the voltage. So we've got to adjust our voltage for temperature. So we're going to go with the coldest. And then we're not going to use VMP, which is the voltage that it operates when it's at its maximum power point. We're going to use the worst case scenario, which is VOC, which is a little bit higher voltage. So when you start throwing in those safety margins, then we might find that 525 that we just did roughly here, it might actually exceed 600. We'd have to look at that. it might not work. It'd be close. But so those are things when we start putting in all of our fudge factors. That's the thing that the inspector is going to look at. If he's a good inspector, he's gonna say, did you do the math correctly? 99 times out of 100, you'll know more than the inspector knows, and they're not going to catch it.
Right.
They just don't know anything about solar.
Right.
But they do know about grounding and bonding, and they're gonna hitch on that if you don't do your bonding and grounding system properly. So now using our scenario here, if we're talking about wire sizing, let's say that I'm doing this. I should have kept that up there. I'm going with 2 strings. I decided each of these strings has 9 amps, right? I'm going to combine them in parallel. Now I'm going to go down here to my DC disconnect. It's going to go into my inverter. From the inverter, it's going to go to my AC disconnect. And from there, I'm going to go into my service panel. All right, we already said that this was going to be 35. So the voltage was going to be 525. Right? 525 volts, 9 amps, 2 strings. So how many watts is this going to be? Well, it's going to be 525 volts times 18 amps. Notice how that power equation comes into play. Watts equals amps times volts. 525 times 18. So this is going to be a 9,450 watt array. Not an out of the question size of an array for a residential building.
Yeah, that seems like a lot to me. But
It'd be a big house, but this would generate maybe about $150 worth of electricity a month. So that's not unusual. You know, I mean, you start, the average is going to be in the neighborhood of, in this region, we'd be looking at a 6,000 or 7,000 watt array. That would be an average residential home. So this is slightly bigger than average. All right, so let's size our wire. Well, the wire that goes between the panel and the combiner box already comes pre-attached to your solar panel, and that's going to be 12 gauge wire. Well, we want to look at the table that I've reproduced here in your book, and I just need to find it. It's, page 111. So this is the ampacity table. So if we look at page 111, and we know that we're dealing with 12 gauge wire, well, what's the maximum ampacity that 12 gauge wire is supposed to be able to handle? Well, if you look at those columns, it's basically saying, okay, it depends on which type of wire you're using. Are you using low heat wire like TW or UF wire, underground feeder, for instance? Are you using a medium heat wire? Or are you using a high temperature wire like PV wire or THHN, THHW used to, those kind of things. Low temperature, 20 amps. High temperature, 30 amps for 12 gauge. But when you're looking at this table, I want you to get in the habit of only looking at column 1 for your ampacity. Go with the lowest case because your connection is not only the wire, but it's the terminals on each end of that wire as well. And those have temperature ratings. And you don't necessarily know what they are. So if they're high temperature, great. But if they're low temperature, that becomes the weak part of the system. So always assume the lowest. So 12 gauge wire, we're going to assume 20 amps. That's what it can handle. Okay, everybody with me that so far?
Yeah.
So what we're doing here is we know that we're going to be transmitting 9 amps. But that's 9 amps at IMP. What's ISC? Well, if we look at the spec, maybe it's say 9.6 amps. It's going to be a bit higher. That's the theoretical maximum. So that's the number we're going to be using when we're sizing our wire because it's the worst case scenario. Then the National Electrical Code says, oh, we want you to put a further safety margin of 1.25. So we take 9.6 times 1.25 and we get 12. But then they say, oh, this is solar. We want you to do an additional 1.25 safety margin. And why is that? It's because this number was determined based on 1,000 watts per square meter, which is standard test conditions. Well, I've taken measurements out in the field and gotten 1,200 watts per square meter on a nice clear day. At the outside edge of the Earth's atmosphere, it's like 1,360 watts per square meter. So if you just get a nice clean day, like here in Southern Ohio, where everybody is, where we're always, the air is pure and people are kind, right? Then you're going to get higher. So we take the second safety margin times 1.25, and now it's saying 15 amps. So our wire better be able to handle 15 amps. Can it? Well, it's 12 gauge. Yeah, it's designed to carry 20 amps. So we're fine. Now let's assume we put a breaker in here or a fuse. What size fuse are we going to use?
15 amp.
Right. You round up to the next available size as long
Yep.
as it's less than the capacity of the wire. So 15 amps. So we'd have two 15 amp breakers or four 15 amp breakers there. The wire is rated for 20 amps, but the breaker is going to trip at 15. So we protected the wire. Not a problem. Now we're hooking them up in parallel. So what's the output of this? It's going to be 2 times 15, 30 amps. So what size wire do we need? At minimum, 10 gauge.
10 gauge.
Right? I'd probably be comfortable with 10 gauge because we got a lot of safety factors in here. So really, we know that we're actually probably going to be putting out 18 amps because we know that the ampacity is 9 at the IMP, and there are 2 of them. So it's probably going to be running 18 amps. But with all our safety margins, we've got to have 30 amp wire. So we're going to put in 10 gauge wire. Now you would have to do your voltage drop because 10 gauge wire may not be big enough like we just saw before, depending on the distance because of voltage drop, but it's big enough for ampacity. Okay, so then we come in here. Well, what size DC disconnect do we need? Typically, DC disconnects come in 30 amp, 60 amp, or 100 amp sizes. So the minimum we would need is a 30 amp DC disconnect. If we're putting a breaker or a fuse in here, we need a 30 amp breaker or a 30 amp fuse, right? Because we round up to the next available size. Now we go into our inverter. What size wire do we need when we leave the inverter? Well, now the whole world changes because we're transferring it from DC to AC, but we're also leaving with 240 volts AC. Well, we came in at what, 525 volts? So at this point, we need to know what size inverter we have. Well, this was a 9.45 kW array. And for a lot of reasons, let's just assume we put in a 7.2 kW inverter. These two are related, but they don't have to be the same. We'll get into a thing called clipping, where usually you're going to put a smaller inverter in compared to the array. And there's good reasons for that, which we'll get into. But let's say we put in a 7.2 kW inverter. Well, if it's 7.2 or 7,200 watts, how many amps? Well, watts equals amps times volts. I can take my watts and I can divide it by my volts to get my amps. So 7,200 divided by 240 gives me 30, right? 30 amps. leaving. But we have to multiply that times 1.25. That's our NEC safety margin. We got to re-put that in. We no longer have to put in the solar variability margin because it's no longer variable. It's being controlled by the inverter. So 30 times 1.25 is 37.5. So the wire here is 37.5 amps. We look at our table there on 111 and we decide we got to put in 8-gauge wire, right?
Yep.
Because it's rated to 40 amps,
40 amps.
right?
Yeah.
So now my AC disconnect, is it 30, 60, or 100 amps rating? Well, which one would I need?
Probably
60.
60, yeah, minimum of 60. I could put in 100. It's not going to hurt anything. If I'm putting in a fuse or a breaker here, what size fuse or breaker?
40
That's-
amp.
Yeah, I
40.
put in a 40 amp breaker because I round up to the next commercially available size. 37 and a half, they don't make those. So 40 amps the next one. Now, does anything change in the wire between the AC disconnect and the breaker?
It'd have to be bigger, wouldn't it?
Well, what does a disconnect do?
Automatically shuts off the system.
Well, no, not automatically. This is a manually operated.
Oh, okay, manually. Okay.
So it's just a light switch, right? Nothing changed between here. It's just that I can either turn it on or turn it off. So this is still going to be 37.5 amps.
So you could still stay with the 8-gauge?
Yeah, so I'd still use 8-gauge wire. And then what size breaker would I put here in my service panel?
40.
40 amp double pole breaker, right? There you go. We just designed a system. So this is how you size your wire. You start there with the panel specs. That's why we need to understand what we're looking at there. And then we just walk through the system and selected every single component. Not quite that simple, but we're getting there. We're close.
Yeah.
So
Cool.
Could
All right.
that wire be could the wire be bigger? Or
yeah,
would
it
you
could
wanna
it
say-
could always it can always be bigger. Yeah.
Okay. Okay.
Yeah, you can always put in bigger wire. The problem is you're spending money you might not have to spend. And if you get too big a wire, it can be really hard to pull through the conduit and it can be really hard to terminate in those pieces of equipment. A lot of them have lugs and the lugs will say what size wire they can handle. Like it might only be 2-gauge wire might be the biggest it can handle. Or it might be 4/0. Who knows? 4/0 wire is pretty big wire. So if you've ever tried to pull wire through a conduit, it can be tough. So, that's part of what you're looking at. And of course, the bigger the wire, the bigger the conduit. So you keep adding costs all along the way. But if you're future proofing, that's a good example there. Let's say, let me see if I've still got my whiteboard here. Yeah, that's still there. All right. So if I've still got my whiteboard here, and let's say we decided this is the roof surface, and this is the size we decided on. It's not a bad idea to size your wire, like calculate what size array your roof could handle. I just got rid of that. Yeah. So if you're only taking up maybe a third of the roof with your 14 kW array, and if you expanded it out to the whole size, then design your wire for that whole size. Even though you only need the 14 kW, so maybe we could get by with 10-gauge wire. But if you went and filled up that whole roof plane, maybe you'd need 6-gauge wire. I would do it. I would do it now. because you never know people's decision-making process. Things change, and it might cost you a couple $100 more to put in the bigger wire and the bigger DC disconnects and things like this at this moment. But if you decided, or the homeowner decided, oh, let's go ahead and add another 14 kW to our array because we just bought an electric car, or we just had a baby, or a teenager moved back home and he's eating us out of house and home, whatever. Well, instead of adding a couple $100, now you're adding thousands of dollars. You're going to have to pull out all that wire. You're going to have to re-pull wire. This is what's known as future proofing. So when I'm designing a rooftop system, I would say design the wiring system as if you're filling up the whole roof with solar panels, because never hurts. Where it does hurt, I guess, I say it never hurts, and then I'll tell you where it hurts, is if you're going into competitive bidding and your job comes in higher than your competition because you're future proofing and they're not. So if you're going to do it, give them both prices. Say, I would recommend you do this, and it's going to add $400 to the cost. We can do it the other way and it'll work, but this would be money well spent right now. Just to handle any future issue. And you'll find some customers, yeah, that just makes total sense. Let's do it. Other customers, nope, I want to get by as cheap as I can get by. And then they'll probably blame you later for not suggesting it, even though you did. And, that's another thing which we haven't gotten into chapter 6, but when we get into that for site assessments, be sure to take a lot of pictures. Take a lot of pictures of everything. Especially if there's already damage, like a broken window or something, because sure enough, the person is going to say you did it after you were on the site. And it's good to just have documentation saying, no, look, that was already damaged. We had that happen here they came and took some trees out. And the guy brought me over and said, look, your next door neighbor, this window here, it's broken. And he said, okay, fine. I was like, you're being paranoid. And he goes, well, we haven't even moved in our equipment yet. It's still broken. I said, okay, fine. Great. I'll take a picture. Sure enough, 2 weeks later, he called me up. You remember I said that window was broken? They're claiming I broke it, and it's like, they want me to replace their window. And it's like, no, they're just being jerks. So anyway, okay, well, we've gone past our time, but again, we'll meet again next Tuesday let me just double check because calendars are getting filled up. So that'll be June 3rd, right?
Yep.
Okay. All right. Chapter, and I'll go ahead and post this, and and we'll see you all next week. And in the meantime, if you run into any questions through the week, don't hesitate, send me an email. That's usually the best way to get me.
Right.
All right.
Okay.
Take care.
You.
All right.
Thank
Sounds good. See ya.
Bye-bye.
See ya. Bye.